Sutuna, and they are my team members. She is 1 and he is we present the design of a Warren Truss bridge using SAP 2000 application. And we have some few objectives. The objective is to utilize our knowledge of like tension, compression, fatigue failure, bending of beam, and end reaction of beam. And then using SAP 2000 software, we designed our virtual model and analyze it sophisticatedly. We used physical model to display the virtual model and then test it. And using the both kind of bridge, we try to make a Warren Truss bridge which can support like, a certain weight of a truck. And this is how we followed a sample of instruction, and we use SAP 2000 to produce the virtual model. And in that application, we selected 2D truss, and we choose 4 bays which were connected to each nodes, and we select 3 load cases and analyzed it. The defined load was 32,000 lb and 8,000 lb. Some of the members of the bridge could not bear that much weight, so we changed their cross-sectional area. And this application shows the failing member in different color. So when it shows red color, that means we have to increase the cross-sectional area, and when it shows blue, that means we have to decrease the area. And thus we make a safe model, and then we export our data to Microsoft Excel. This first picture shows that 16,000 lb in the first 2 joints and 4,000 lb in the third joint, and this is the first defined load. And in the picture 2, the defined load is in like second and third joints, which is 16,000 lb and 4,000 lb in the fourth joint. This is the third picture, which shows like 16,000 lb in the third and fourth joints and 4,000 lb in the last joint. Picture 4 shows 16,000 lb in the last 2 joints. And after building the virtual model, we build physical model. We use trunk depressors. The cross-sectional area which is more than or equal to 20, we use 3 trunk depressors for that. And for cross-sectional area which is between 5 to 10 meters, we use 2 trunk depressors, and 1 for the cross-sectional area which is less than or equal to 4. Then we made the deck with flat trunk depressors and then glued together with longitudinal members. At last we screw all the members and use screw and brackets to hold them all together to their joints. And this is the picture which shows different cross-sectional area of different members. The red area and the yellow area shows this area must be bigger. The cross-sectional area should be bigger. And this is my procedure.
Final prototype was built based on the virtual model. So as you can see on the picture, the whole top and the diagonals on the 2 sides have very big cross areas. So on the space we put 3, and the member in the middle has the biggest cross section area. So we put 4 here, and the cross section area of the rest beams were not as big as the top. So we usually put 2. But then the second and the third bay has the larger cross section area. So we put 3 here. The diagonals between the 2 and second, which means those 2 has no very small cross section area. So we only put 1. So cost evaluation. as we know the height and the division length, so we know by the calculation we know that all the lengths are constant, which is 1575 feet. Converter unit, we know that it's 189 inch, which you can find in the third column. According to the length of the beams, we can find their cross-section area. In all, by multiply the third and fourth row, we can get the volume of the steels. By multiply the volume of the steel times multiply the volume of the steels by the density, we can find the weight of the steels. So the last step is the multiply the weight of the steels times the specific heat, the cost of the steel per 20 kilo pound, 20,000 pounds. We can get the cost of the steels. Add up the number of the this column, we can get a total cost of the steel. So our cost of the steel is 5,407.
Okay, next I will present the discussions and conclusion. For discussion, we are focusing on the difficulties we face in this project and what we learned from this experiment. For the virtual models, it's hard to balance the cost and safety in the virtual models, which means it's hard to change all the color from blue or yellow to green. And next one is how to understand the data we export from the software and collect the useful information. Last one is how to use the virtual models to build up a physical model. And for the physical models, the materials are flimsy, and we need great care in connecting each bridge member, otherwise it will make the physical models become unstable. And what we learned from this experiment is how to use SAP 2000 to build a virtual model, and how to calculate total cost of the bridge by knowing the cost of each member. And next one is the conclusion. For the conclusion, I will focus on the advantage of the virtual models and the physical model. For the advantage of virtual model is repetition of text is easy, because you can repeat the text as many times as you want, and you won't produce actual cost. And the second one is able to specify and read exact values. And moreover, based on the different condition we have, we just simply change the force applied on the bridge members, and maybe we change the whole structure of the bridge. And the next one is least time consuming. Of course, it just only take like 15 and 20 minutes to build up the virtual models. And next is the advantage of physical models. The first one is can be easily relate to and perceive what happens in the real world. For example, the graph in the virtual models. For people who never used software before, will have a hard time to understanding what this number means and what this color indicates. But for the physical model, we just need to put a text weight on it. If it crash, we know which part is safe, but which part need to be reinforced. And next one is can avoid learning complicated software package. The final one is result can be interpreted easily. Like what I mentioned before, you just need to text it and see which part need to improve. And that's it. Thank you.
No. Any question?
No.
Yeah, I tell you,
Yeah, thank you. You were talking about, at your final stage, you tried to talk about the advantages of the virtual model and the other things.
It's physical model.
Also, so how did the virtual model influence your design in your physical model? How does it influence your physical model?
Like in the virtual model, we know the cross section of each member, right? And according to the data, we build up the physical models. Like if the cross area of this part is big, then we know we need to use more material for this members.
Okay, thank you.